a single freight train stretching 4 miles across the Australian desert, nearly 700 wagons, over 80,000 tons of iron ore, pulled by locomotives spaced miles apart and coordinated by radio telemetry. These Pilbara ore trains are among the longest and heaviest ever operated on Earth. The United States has a rail network 10 times larger and moves more freight than nearly any country on the planet. Yet American trains rarely stretch beyond 1.5 miles. The technology to go longer already exists. America has it. So the question isn't whether the US could run 4-mile trains. It's why the entire system is built so that it doesn't. The United States operates a massive rail network encompassing roughly 140,000 miles of track, making it one of the largest and most productive freight systems on Earth. This network is nearly 10 times larger in total mileage than all of Australia's railways combined. Yet despite this vast geographical reach and the sheer volume of cargo moved daily, American freight trains remain relatively modest in length. The median freight train in the United States measures just 5,300 feet, slightly over 1 mile. Even when American railroads assemble their largest consists, they rarely exceed the historic boundaries of the domestic infrastructure. The Association of American Railroads formally designates any consist over 7,500 feet as a long train, a threshold that remains the operational baseline for most carriers. This stands in clear contrast to the Pilbara region of Western Australia, where iron ore trains routinely stretch past 4 miles in length. This gap does not exist because of national size, engineering capability, or freight demand. The American system is a global leader in logistics, moving billions of tons of agricultural products, consumer goods, and industrial materials every year. Instead, the physical reality of the United States network keeps train lengths firmly capped. To understand why these systems diverged, one must look at how the American network functions as a single, interconnected system. Running a 4-mile train in the United States requires more than coupling additional locomotives and wagons. The entire operational environment of the country's rail lines, from the physical layout of the tracks to the daily coordination of diverse traffic, is built for a different set of priorities, preventing the adoption of the extreme lengths seen in the Australian desert. The constraints are built directly into the system itself, shaping every dispatch decision and route limit from coast to coast. This physical and operational structure dictates train lengths long before a locomotive even leaves the yard. Train length is determined by system design rather than engineering ambition or technological capability. In theory, any railroad can couple dozens of locomotives to hundreds of cars and pull them forward. The actual limit of a train is dictated by the infrastructure system supporting it in routine service. 4 core structural pillars govern this limit: the ownership model of the tracks, the type of cargo being hauled, the physical geography of the route, and the operating rules that govern daily traffic. The first and most critical pillar is ownership. When a single entity owns the entire line from origin to destination, it controls every variable. There are no competing operators, no passenger timetables to accommodate, and no third-party shippers demanding priority. The tracks can be tailored for one specific task. The second and third pillars, cargo and geography, work in tandem. Moving a single, heavy bulk commodity like raw ore requires a vastly different logistical footprint than hauling a mixed assortment of consumer goods, chemical tanks, and agricultural products. When this uniform cargo travels over flat, isolated terrain, the physical forces acting on the train remain predictable. Without steep climbs or sharp curves to strain couplers and break steel linkages, physical constraints on length begin to fall away. Finally, operating rules act as the ultimate filter between what is physically possible and what is practically sustainable. In a complex, shared network, a train must constantly interact with passing loops, signaling blocks, and maintenance windows. If a train exceeds the physical capacity of these operational features, it ceases to be an asset and becomes a bottleneck. Ultimately, a train does not operate in a vacuum. Its length is always a direct reflection of the boundaries of the system it inhabits. The practical application of this vertically integrated system is found in the red dirt of Western Australia's Pilbara region. Here, the world's most massive heavy-haul rail operations are defined by three major corporate entities: BHP, Rio Tinto, and Fortescue. These companies do not operate as common carriers. They do not rent track space from public agencies or haul mixed goods for external clients. Instead, they are mining companies that designed, constructed, and now operate their own heavy-duty rail lines as single-purpose industrial arteries, built solely to transport iron ore from remote inland pits to coastal export terminals. This private infrastructure was constructed in distinct historical phases to meet the needs of international steel production. The foundation of the modern Pilbara heavy haul model began with the opening of the Hamersley Railway in 1966, followed by the Mount Newman Railway in 1969. The regional network expanded further with the completion of the Robe River Railway in 1972, and was later reinforced by the Goldsworthy Railway in 1993. More recently, Fortescue established its own massive rail corridors, securing independent access to the coast. Today, these corridors represent a multi-thousand-kilometer network of private standard-gauge track. By keeping both the track ownership and the train operations entirely within the same corporate structure, these miners eliminated the operational compromises that define shared-use railroads. A single company manages the entire logistical chain from start to finish. The same organization that extracts the raw ore also runs the loading bins, dispatches the trains, maintains the physical track, and manages the unloading infrastructure at the port. This means there are no passenger schedules to accommodate, no local commuter services to clear, and no competing freight operators to coordinate with. Because the railway serves only one customer and carries only one commodity, train scheduling is coordinated entirely around mining output and ship arrivals. This absolute vertical integration converts the railway from a public transit corridor into a private, high-capacity conveyor system, treating the tracks not as a shared utility, but as a direct physical extension of the mine itself. A single-purpose railway functions on a fundamental principle: absolute simplicity of traffic. On the private heavy-haul lines of the Pilbara, there are no passenger trains running to fixed public timetables. There are no commuter services demanding track priority during morning rush hours, and there are no general manifest freights carrying mixed goods, hazardous chemicals, or agricultural products for multiple third-party clients. Every wheel that turns on these tracks is dedicated to moving iron ore. This total isolation of traffic removes the operational friction that degrades capacity on shared networks. On a typical multi-use railway, dispatchers must constantly resolve conflicts between fast passenger services and slow, heavy freight trains. In the Pilbara, every train moves at a uniform speed, carries the exact same cargo, and shares identical handling characteristics. This extreme homogeneity allows the mining operators to space trains closely and run them with clockwork predictability, maximizing the daily throughput of the entire line. There are no delays caused by waiting for a higher priority train to pass, and no yard bottlenecks created by sorting different types of freight cars. The isolation of these corridors extends to their physical interaction with the surrounding environment. The Pilbara's desert routes traverse vast, sparsely populated territory, with almost no highway rail intersections. While the United States rail network contains more than 212,000 public and private grade crossings, the Pilbara lines are virtually clear of them. This near-total absence of level crossings eliminates the risk of vehicle collisions and removes the public safety requirement to limit train lengths to prevent blocking local roads. With no crossings to clear, no passenger trains to avoid, and no competing freight traffic to accommodate, the entire railway operates as an uninterrupted industrial conveyor. Maintenance windows can be scheduled with absolute precision, ensuring that the heavy wear of 40-ton axle loads is managed without disrupting third-party operators. Every piece of infrastructure, from the ballast bed to the signaling system, is engineered for one task: hauling tens of thousands of tons of ore in a single movement. By stripping away the complex compromises of a public transport network, the operators have created an environment where train length is determined by structural necessity rather than administrative constraint. The physical geography of Western Australia's Pilbara region acts as a natural partner to heavy-haul engineering. The railway corridors run through vast, flat, and straight expanses of sparsely populated desert, providing a blank slate for rail design. Unlike traditional routes built around pre-existing cities or complex geological barriers, these industrial tracks were laid with a single geometric priority: maintaining a straight line with minimal elevation changes. The corridors connecting inland mining hubs to coastal ports cover massive distances, typically ranging from 400 kilometers to 1,700 kilometers. Across these vast reaches, the physical grades are kept remarkably gentle, generally remaining under 1%. By avoiding steep climbs and sharp winding curves, the physical forces acting on the couplers and steel structures of the train remain low and predictable. This favorable geometry is supported by a specific directional flow. The major iron ore mines are situated in the high inland ranges, at a higher altitude than the coastal export terminals. Consequently, the loaded trains, carrying tens of thousands of tons of raw ore, travel downhill toward the coast. Gravity assists the locomotives rather than opposing them, meaning the heaviest pulling force is not needed when the train is at its maximum weight. Once the ore is discharged at the ports, the return trip inland requires the locomotives to climb back up the elevation gradient. However, these returning trains are completely empty, consisting only of empty steel wagons. The locomotive engines only face the uphill climb when their overall tonnage is at its lowest. This division of labor, loaded downhill to the sea and empty uphill to the mines, minimizes physical strain on the track and the rolling stock. In a standard rail network, trains must constantly battle varying topography, climbing steep mountain passes, and rounding tight curves while fully loaded in both directions. In the Pilbara, the terrain itself is integrated into the operational design. The terrain functions as an active component of the machine, creating a physical environment where 4-mile trains can run smoothly without geography tearing the cars apart. Pulling a 4-mile train requires managing immense physical forces. If all the locomotives sat at the very front of the consist, the tension on the first few couplers would exceed their structural limits, snapping the heavy steel linkages instantly. To prevent this, operators distribute locomotives throughout the consist. These remote locomotives, known as distributed power units, are placed mid-train or at the rear. A proprietary radio telemetry system called Locotrol coordinates these remote units, allowing a single driver in the lead cab to command traction and braking simultaneously. Wireless signals transmit throttle and torque adjustments down the line within milliseconds, ensuring that all engines work in synchronization. Spreading the power throughout the train alters the physical forces at play. Instead of a single locomotive pulling the entire weight from the front, multiple units push and pull specific segments of the train. This reduces in-train tension, which can tear couplers apart on steep grades, and limits compression, which can cause cars to buckle or derail during deceleration. Managing this slack action keeps the massive payload stable and prevents individual wagons from moving independently. The reality of these physical limits became clear during BHP's record-breaking run in June 2001. As the 682-wagon train climbed the Chichester Ranges, a single defective coupler failed under the strain. The brakes stalled the run for nearly 5 hours, requiring 2 extra locomotives to push the remaining wagons over the summit before the journey could continue. To further control these forces, heavy-haul railways use electronically controlled pneumatic brakes. Traditional air brakes rely on air pressure traveling down a physical pipe, creating a lag of several seconds between the front and rear wagons. Electronically controlled pneumatic brakes use electrical cables to send a signal that applies the brakes on every wagon at the exact same instant. This simultaneous application cuts peak coupler forces by up to 15%, preventing the heavy rear wagons from crashing forward and causing a derailment. By coordinating the push of multiple engines and the simultaneous squeeze of hundreds of brakes, wireless technology holds these 4-mile giants together. American railroads possess the exact same technology used to run 4-mile trains in Australia. The locomotives pulling freight across the United States are built by the same manufacturers, primarily General Electric and Electromotive Diesel. These Class 1 carriers use identical distributed power systems, wireless locotroll telemetry, and electronically controlled pneumatic braking. The physical capability to couple hundreds of steel cars together and haul them across a continent is not in dispute. In fact, U.S. operators have periodically assembled experimental trains stretching miles in length, proving that American engineering can handle the extreme physical forces. The divergence is not a question of capability, but of environment. A railway is not an isolated physics experiment. It is a system built to solve a specific geographic and economic problem. While Australia's Pilbara railways exist solely to move a single bulk commodity from a private mine to a private port, the American rail network must balance a wide variety of competing obligations. The 140,000-mile U.S. network is a shared utility. On any given mainline, a single operator does not hold exclusive control. Freight trains carrying agricultural products, chemicals, and consumer imports must share the same steel rails with passenger services and local commuter lines. Managing these diverse traffic flows requires a constant series of operational compromises. In this environment, extreme train length ceases to be an efficiency triumph and becomes a system bottleneck. The true constraints on American train lengths are built not into the locomotives, but into the crowded territory through which they must travel. The 140,000-mile American rail network operates as a giant shared utility. Unlike the isolated single-user lines of the Pilbara, U.S. tracks are crowded corridors where massive freight trains must physically coexist with passenger and commuter services. This shared reality is not an occasional exception. It is the daily operating standard for major Class 1 carriers like BNSF, Union Pacific, Norfolk Southern, and CSX. According to Amtrak data, more than 70% of its nationwide mileage is operated over tracks owned and maintained by private freight railroads. This means that a mile-long intermodal or bulk freight train is rarely alone on the line. It shares the same steel rails with high-speed passenger cars carrying thousands of commuters and travelers. To make this cohabitation work, federal law establishes a strict hierarchy of movement. Under the statutory common carrier obligation, freight railroads are legally required to grant passenger trains dispatching preference. When an Amtrak service approaches, dispatchers must ensure its path is clear, often requiring heavy, slow-moving freight trains to step aside. In a dense corridor, a single dispatcher manages a complex puzzle. They must slide high-priority, fast-moving passenger trains through a series of blocks while keeping slower, heavier freight trains rolling. Introducing an exceptionally long train into this delicate system disrupts the entire rhythm. A train of that scale occupies multiple signaling blocks simultaneously, effectively blinding the dispatch system and blocking potential paths for passenger runs. The system is designed for high-frequency coordination, not massive, slow-moving monolithic blocks. Every dispatch decision is a trade-off, balancing the transit times of time-sensitive consumer imports and Amtrak schedules. In this environment, train lengths are kept modest to preserve the flexibility required to keep the entire nation's diverse traffic moving. The physical limit of any railroad network is ultimately governed by the length of its passing sidings. Across the United States, the vast majority of mainline passing sidings, the parallel tracks used to let trains pass one another, measure between 7,000 and 10,000 feet. This range represents the historical design envelope of American rail infrastructure, built for an era when one-mile trains were the absolute standard. While some Western railroads have invested heavily in extending select sidings to 16,000 feet to accommodate longer consists, these mega sidings remain exceptions on an otherwise constrained national map. Much of the system still relies on those older, shorter configurations. When a train's physical length exceeds the capacity of the shortest siding on its route, the entire dispatching system faces a mathematical bottleneck. An extra-long train cannot pull off the main line to let a faster passenger or priority freight service pass. It cannot easily be parked, stored, or held in a standard yard track without spilling over into adjacent lines. If two trains of this scale meet on a single track line, they cannot bypass one another. One of them must reverse for miles to the nearest suitable loop, or the dispatcher must freeze traffic across multiple sectors to clear a path. This physical footprint turns network geometry into a hard operating ceiling. A train that is too long to fit into a siding ceases to be an asset. It becomes a rolling roadblock, stripping dispatchers of their other operational flexibility and causing widespread delays across hundreds of miles of shared track. The physical constraints of the American rail network do not end at the siding switches. They spill directly into the streets of thousands of communities. The United States contains more than 212,000 highway rail grade crossings scattered across its rail system. Because these tracks frequently bisect towns, neighborhoods, and school zones, an exceptionally long train occupies valuable space and physically cuts communities in half. When a train stretching 2 or 3 miles slows down or stops, it turns public crossings into impenetrable steel barriers, blocking local traffic, school buses, and emergency vehicles. The consequences of these blockages are immediate and hazardous to public safety. In Thornton Township, Illinois, a suburban community southwest of Chicago, a freight train stopped across a local intersection, blocking a grade crossing for 37 minutes. For over half an hour, local school buses, daily commuters, and emergency ambulances sat idle, waiting for the massive consist to clear the roadway. In rural areas, where alternative detour routes are often miles away, the results can be catastrophic. In the small town of Leggett, Texas, a Union Pacific freight train stopped on Glover Road, blocking the town's single access point for more than an hour. During this 60-minute standstill, paramedics trying to reach a stroke victim were trapped on the other side of the tracks, unable to deliver critical medical care. Later, a local fire crew faced the same barrier while trying to reach an active house fire. These prolonged blockages reveal the direct human cost of running ultra-long trains through a highly populated, densely crossed network. They have fueled intense national debates and federal legislative scrutiny over crossing safety. Operating conditions that work in the uninhabited expanses of the Australian outback become a civic crisis when forced into the middle of American towns, transforming public infrastructure into localized emergencies. Federal safety regulations impose a strict boundary on the human beings operating American freight trains. Under the Hours of Service Act, U.S. train crews are legally capped at 12 consecutive hours on duty. Once that clock runs out, workers must receive a minimum of 10 uninterrupted hours of off-duty rest. In practice, moving a freight train across the country commonly requires a 2-person crew, consisting of an engineer and a conductor. When trains grow longer and slower, they are far more likely to run out of time before reaching their destination. A single delay on a shared corridor can cause a crew to exceed their 12-hour limit, forcing the train to stop immediately on the main line until a relief crew can be dispatched. This operational pressure has intensified under a dominant industry doctrine. A Government Accountability Office report confirmed that 6 of the 7 largest Class 1 railroads in the United States have adopted precision-scheduled railroading, commonly known as PSR. This management strategy prioritizes running fewer, longer trains with reduced staffing to maximize asset utilization. While rail carriers point to improved efficiency, railroad unions and safety inspectors argue that PSR pushes the system to its absolute limits. Labor groups contend that managing massive heavy consists with lean crews over 12-hour shifts, exacerbates crew fatigue, and degrades safety. In this environment, the decision to run a longer train involves a complex logistical equation of federal hours, staffing agreements, and corporate operating philosophies that govern every shift on the high iron. The contrasting realities of American and Australian rail operations reveal that train length is determined by system design, not engineering capability. The physical limits of a train are shaped entirely by the environment it must navigate. Australia's 4-mile iron ore trains exist because of a rare, highly specific alignment of private track ownership, single-purpose bulk cargo, and an empty desert geography. In the Pilbara, the entire rail network is a closed system. The tracks, locomotives, and ports are owned by the mining companies, built from the ground up to move one raw commodity downhill to the sea. There are no passenger trains to clear, no competing freight operators to coordinate with, and virtually no public-grade crossings to block. This absolute isolation allows the infrastructure to be customized entirely for heavy-haul productivity. This operational design makes the Pilbara model a specialized industrial conveyor rather than a universal standard for freight transportation. A multi-use, transcontinental network, like the one in the United States, cannot adopt these extreme train lengths because its everyday mission is entirely different. The American system must move thousands of distinct commodities across a shared, populated network of 140,000 miles of track, balancing commuter lines, passenger schedules, and local road crossings. Ultimately, the divergence is structural and operational. The fact that American freight trains do not stretch to 4 miles is not proof that America is lagging behind. It is the natural, necessary result of operating a highly complex, shared national network rather than a private mining pipeline. Ultimately, infrastructure is destiny. As global supply chains face unprecedented pressure, these rail systems prove that efficiency isn't about copying another nation's triumphs, but mastering your own geography. The American network thrives on shared complexity. Australia's relies on isolated singular focus. Neither is superior, they are simply mirrors of the lands they serve. Which approach is better suited for the future? Let us know in the comments and subscribe for more.